Physical properties of minerals. All right. Let me move my face out of the way. Sorry about that. So recall back that the atomic structure really defines some of the physical properties. We're not going to harp too much on that in this part, but I'm going to define what those chemical properties, those physical properties are. The color of a mineral is going to really depend on the atoms in that mineral and how they reflect light or absorb light, and little changes in the chemistry of the mineral, like for example quartz can be amethyst, or it can be citrine, or smoky quartz, or milky quartz. Little changes in the trace elements within that SiO2 can give us different color minerals, but for the most part the minerals are going to be a certain color, like these in this tray. Streak, luster, hardness, specific gravity, crystal habit, and fracture or cleavage are all part of this physical properties story. So here is color, and there's the different quartz we pick on it. Here's the different examples of quartz: a rose quartz, a clear quartz, and a milky quartz. And just trace elements, trace minerals can change that color. On the right here, left, right, the green one is malachite. And malachite is a copper oxide, and it's always green. It can be found with blue mineral sodalite, and you'll see blue and green splotches, but the malachite is always green. Another physical property is the streak of the mineral. The streak can help sometimes when a mineral can be different colors, or two minerals can be the same color. You can take the mineral and rub it across a piece of unglazed porcelain, or if it's a light colored mineral, a piece of slate. And the streak is the color of the powdered mineral, and it can be a little different. Like this example of hematite, it's a gray, kind of sparkly mineral, but when you put it over the streak plate, it's red, it's reddish brown. So streak is used maybe when the color is not such a diagnostic feature. The next one is luster, and luster kind of is how the mineral reflects light. And we usually start with, is it metallic or non-metallic? So the example is pyrite, and it looks like a piece of metal. So we would call that metallic luster. Above that are two examples, ignore the dog barking, two examples of feldspar. And the feldspar is not metallic. It doesn't look like a metal. So if it's metallic, it looks like a metal. And then non-metallic, from non-metallic, we can classify it a little bit more specifically with, does it look silky or vitreous, like a piece of glass, satiny, like a piece of satin, resinous, like resin, pearly, like a pearl, earthy or just dull, or adamantine. Adamantine is just a fancy word for like brilliant, like a diamond. So luster, also metallic, non-metallic, and then classify a little bit further with those other non-metallic terms. Hardness. Hardness is the resistance to scratch. And the resistance to scratching is all based on the surface of that crystal and how strong the bond is. When you scratch a crystal, it's breaking the bonds between the atoms in the lattice. So here's the table. It's called the Mohs hardness scale. And 1 is talc. It's the softest mineral. You can scratch it with your fingernail. Gypsum, calcite, fluorite, apatite, orthoclase, quartz, topaz, corundum, diamond. Corundum, in parentheses there, it says ruby. So corundum is rubies and sapphires. So normally we will just use our fingernail, which is between gypsum and calcite, so a 2.5. We can use a copper penny, 3.5, between calcite and fluorite. And then a steel knife or a piece of glass is 5.5. Above that, usually it's going to be a steel file. You can use a steel file. It's not something you probably handy maybe in your toolbox, but we can test the hardness of those different minerals. So if you can scratch the mineral with your fingernail or your knife or your file, then the mineral is softer than that hardness. If it doesn't, then it's harder than the hardness of what you're trying to use, like your fingernail, to scratch that mineral. So Mohs hardness scale, breaking those bonds on that surface. Specific gravity is the heft, so we can just kind of heft a mineral and see how heavy it is. Some are heavier than others. It's a representation of the density. It has a real specific gravity, has a specific definition. The mineral weight over the weight of equal volume of water, so we can quantify that value as well. So specific gravity of a galena, that's a lead sulfide, 7.6, whereas quartz is fairly light, just a 2.65. So a piece of metal, galena, is going to be pretty heavy. It's going to feel heavier than quartz for the same volume of the solid. Crystal habit is the shape of the crystal. So we've looked at these before. Sorry, let me turn my face off. A cube here of pyrite. You can have bladed crystals like in the middle, and then over to the right, like really kind of like sea urchin-y splays of radiating crystals. So these needles are kind of fragile, but they're crystals, and yeah, they grow from a central point. So these are going to be reflections of that internal structure of the mineral, right? The atomic array. Okay. Other special properties, there's a long list here. You can read through them, but one we use a lot is whether or not the mineral fizzes with acid. So we can put hydrochloric acid, a little dropper of it, on the mineral calcite, and it's going to fizz a little bit. There's another mineral that fizzes called dolomite. Dolomite is like calcite, but it has magnesium in it in addition to the calcium in calcite. And in order to get dolomite to fizz, you have to scratch it a little bit, expose more of the surface area. So that's called effervescence. Minerals can be magnetic. Minerals can taste different ways. Halite is one in the olden days, we could taste a mineral. We don't do that anymore. It tastes like salt. You might want to do that in the field, but maybe not in the lab. Some minerals can smell funky, like sulfur minerals. Some minerals feel weird, so you can get a weird tactile response to them. They may be able to bend, like a mica can bend. And there's a whole list there of other ways you can test, physical properties you can test for a mineral. Okay, we use those first 5, they were the main ones. Then we can look at the way a mineral breaks. So the way a mineral breaks is going to go back to the atomic structure and the bonds and the strength of the bonds and the directions of the bonds. This example here is quartz, and notice there's like swoops on it. That's called a conchoidal fracture. So there are obsidian also breaks this way. You may think of obsidian breaks that way, but conchoidal fractures, that swooped shape, that's the way it breaks. Okay. Another way a mineral breaks is something called cleavage, and this is the tendency for a mineral to break along a plane of weakness in the atomic structure. So imagine like the NaCl, you have planes in there of atoms and the bonds between them. And remember, graphite had those strong bonds between the sheets of carbon, but weak van der Waals bonds between them. If there's a weakness, then that's where the mineral is going to have the tendency to break, and that's called cleavage. So in this image, this mineral, this cartoon, has cleavage planes, faces, whereas the crystal there has crystal faces. And the direction of cleavage matters. It can be at 90 degrees, like in this example, or other angles to define the cleavage. Look at some examples. Here is muscovite, has one, this is mica, muscovite mica, one direction of cleavage. I'm going to put my face over here. One direction of cleavage, you can put a knife blade between the weak van der Waals bonds that within the sheet of mica they're strong, but between them it's not. That's one direction. Here is pyroxene, has 2 directions of cleavage at 90 degrees. And here is 2 direction cleavage, and an amphibole not at 90 degrees. Those are 60-degree angles in that cleavage. Here are 3 directions of cleavage. Halite makes little cubes, and they're at 90 degrees. And so you would can break it with that's a knife blade, but you can smash it with a hammer. And if you zoom in and look really closely at salt cubes in your kitchen, there's my kitchen, salt cubes in your kitchen, it will all look like tiny little cubes, and those are cleavage planes with the NaCl. Calcite has also 3 directions of cleavage, but the angle is not 90 degrees, so it's like a skewed cube.